So in the last class, we started off with evaluating properties. So properties are, in thermodynamics, the most common properties are temperature, pressure, specific volume. If we know any two of these properties, we can define a state. Which means from two properties we can find the internal energy, enthalpy, entropy, and other properties from two of these states. So does a state help us to define a system? So this can be represented, a state can be represented on a temperature specific volume plot or temperature or pressure versus specific volume plot. So whenever you have to draw a state, you first draw the axis, you label the axis, temperature versus volume or pressure versus volume. Then you draw this vapor dome on both of them. So a dome, meaning of dome is a small mountain. So you draw a vapor dome. After drawing it, you need to draw for temperature versus volume the line of constant pressure. And for pressure versus volume, you need to draw a line of constant temperature. So you have to draw these lines. There is no need to draw for temperature versus volume the line of constant temperature or line of constant specific volume, because you are familiar with that a line of constant temperature would be a horizontal line. Line of constant specific volume would be a vertical line. So you draw a line of constant pressure. So how can you understand this line that has been drawn? So suppose you have a piston cylinder having initially
सर स्क्रीन
what?
शो नहीं हो रही.
So suppose you have a piston cylinder having water in it. So a piston cylinder having water in it, and you start applying heat to it. So the temperature of it would start rising. So this region on the left hand side is called the subcooled region or the liquid region. As you start heating it, the temperature of the water will rise. So it will reach the boiling point of water, and after that, as you keep on adding heat, the temperature of it would remain constant. After that, if you want the pressure to remain constant, then after reaching the superheated region, it would again start increasing the temperature. So I would like you to remember that the first step is that you draw the axis, you label the axis. The second step is that you draw this vapor dome. And the third step is that you draw the line of constant pressure or the line of constant temperature. So before we move on, we went through this formula of quality. Quality is the mass fraction of vapor inside a mixture. So it is the ratio of the vapor present divided by the total mass. The total mass comprised of liquid and vapor. So the left side of the vapor dome is saturated liquid line. Saturated liquid line means that it is 100% liquid. The right line is saturated vapor line, which means that it is 100% vapor. So quality on the left hand side on this line is 0 and the quality on the right hand side is 1. So suppose we have this TV diagram and we have a mixture which is some of it is liquid, some of it is vapor. It is in the mixed region. So the specific volume of it is volume divided by mass. So a mixture having liquid and mass and vapor. So the specific volume of it is V liquid divided by M plus V vapor divided by M. Now the V liquid is mass of liquid into specific volume of the liquid, which is represented by F. So the specific volume which is on this side of the vapor dome, that is called Vf. Vf means the specific volume of liquid, or you can say specific volume of the fluid. F is for fluid, so specific volume of the fluid. And this specific volume over here is the specific volume of the gas or vapor. So instead of V liquid, they have substituted the value of V liquid, which is mass of liquid, into specific volume of the liquid, and mass of vapor into specific volume of the gas or vapor. Now in the last slide we learned that the quality is the mass fraction of the vapor divided by M, and mass liquid over M is equals 1 minus X. So substituting the value of mass vapor substituting this equation number 1 and equation number 2 into this original equation, so we get this equation, which is V equals Vf plus X into Vg minus Vf. So specific volume equals Vf plus quality into Vg minus Vf. So how does this equation make sense? So this is again a vapor dome. The volumes on the left hand side are called Vf. The volume on the right hand side are called Vg. Suppose we have a mixture which is in between the dome. So we have to get to this point. So this point is the summation of this distance and this distance. So up till this point it is Vf. From point 1 to 2, so the total distance 1 to 3 is Vg. From 1 to 3 the total distance is Vg minus Vf. So if we want to get to 1 to 2, we multiply X, the quality, with the total distance, which is Vg minus Vf. So we get the specific volume of the mixture. Next is enthalpy. So enthalpy is the total energy. Enthalpy is the total energy at a state. It has two components: internal due to temperature, PV due to flow work. Internal due to temperature, PV due to flow work. So if we divide the entire equation by mass, we would get the second equation in which all the terms are per unit, and if we divide by mole, we get this equation in which all the terms are divided by mole. Now for mixed state, we get internal energy which was similar to the specific volume that we derived, that U equals UF plus quality into UG minus UF. H equals HF plus X into HG minus HF. So both these equations are for the mixed liquid vapor region. Now so we bring to the first question regarding the properties. Read this question and try to understand it. So we have to determine the phase or phases in a system consisting of H2O at the following condition and sketch a PV and a TV diagram. So they have given us pressure and temperature and they are asking us to determine the phase. Phase means that is it liquid, is it vapor, is it liquid and vapor? And they want us to draw a sketch on a PV and a TV diagram. So the first thing is that we do is we draw the axis, so PV and TV. Then we draw the vapor dome, and then we draw line of constant temperature and line of constant pressure. Now by looking at this, we are solving part A. By looking at it, we cannot determine that which is it here, is it here, is it here, which region is this point at. So we need to use the tables which are present at the back of the book. So now you can see the book that I have opened. So I'm in the table of contents. Now you can see on the right appendix tables, figures and charts. The first tables, index to tables in SI units, page 925. Then we have index to tables in English units, page 973. So from 925 to 973 we have tables in SI units. In this course we would be using SI units. So let's go over these tables. So on page 925 we have index to tables. I want you to go over this table on your own as well and try to understand it. So all of these tables are in SI units. Then table A1 is the atomic or molecular weight and critical properties of selected elements and compounds. So table A1 has atomic and molecular weights and critical properties of selected elements and compounds. Table A2, properties of saturated water, liquid vapor, temperature table. So it has saturated water Saturated water means that it has properties which are of vapor dome of the liquid as well as vapor. So remember that there was a left side of the vapor dome which was saturated liquid. So it has properties regarding that as well as saturated vapor. Then properties of saturated water, liquid vapor, pressure table. The only difference between A2 and A3 is that A2 is temperature table, A3 is pressure table. The meaning of temperature table is that all the properties are with respect to temperature. When you will open table A2, the leftmost column would be temperature, which means that if you know temperature, you can find other properties. And table A3, you have pressure table. Then table A4 is superheated water vapor. So superheated water vapor is the right hand side of the vapor dome. Table A5 is compressed liquid. So that is the left hand side of the vapor dome. Then A6 is saturated water solid vapor temperature table. Table A7 is similar to table A2. Difference between is table A2 had water, table A7 has refrigerant R22. Table A8 is similar to table A3. The difference is that the working fluid is different. Similarly, A9 is similar to A4, that it is superheated, but the working fluid is different. Now A10 to A12 is similar to A2 to A4 table. The difference is the working fluid. The same repeats for then we have from refrigerant 134A we move to ammonia. So table A13 to A15 is ammonia. Table A16 to A18 is propane. Now we move from this saturated regions to properties of selected solids and liquids. So table A19 we have Cp, rho and K. Cp is specific heat capacity, rho is density, K is thermal conductivity of solids and liquids. Table A20 we have ideal gas specific heats. So table A20 has Cp again, but for an ideal gas. So table A21 we have variation of Cp with temperature. Table A22 we have ideal gas properties of air. Table A23 ideal gas properties of selected gases. Then we have constants, van der Waals constant, Radley, Kwong, Benedict, Webb, Rubin, equation of states. Table A25 we have thermochemical properties of selected substances. Table A26 we have standard molar chemical exergy of selected substances. Table A27 we have logarithms of to the base 10 of equilibrium constant. So there are many tables here. The tables that we will mostly be using would be table from table A1 to table A19, A1 to A19 and A22 and A23. So after going through the index, go on it on your own. Now let's look at the problem. So we have water. In the question we had water as the fluid. So the tables that are relevant to our problem are water tables are from A2 to A5. So A2 to A5. So we know temperature and pressure both in this question. We know temperature and pressure both. So all of you write this thing down. The temperature that we have is 179.9 degrees Celsius and the pressure we have is 10 bar. So if we go to table A2, the temperature is 179.9 degrees Celsius. If we keep going down, we have 180 temperature in the table and the corresponding pressure. The corresponding pressure is 10.02. All of you write this thing down, that corresponding to 180 we have 10.02 bar. Now if we go to pressure table, we have this leftmost column is that of pressure. So here if we keep on going down, the corresponding to 10 bar we have a temperature of 179.9 degrees Celsius. So what does these table values mean? So what does it mean is that corresponding to 10 bar, the table said that the temperature is 179.9, which basically meant that if this line, horizontal line, is 10 bar, the temperature here would be 179.9, and if here this line is 10 bar, this temperature is 179.9. So the table tells us the saturated liquid state. So in table A2 and A3, what the tables tell us, it tells us the saturated liquid state. It tells us information for this region, this region inside the vapor dome, that if we know pressure, we can get the corresponding temperature. Now let's look at part B. So in part B, we have a pressure of 10 bar and a temperature of 150 degree Celsius. So in part B, we have 10 bar. So I would solve part B on part what I've already drawn for part A. So a pressure of 10 bar. So I've already drawn 10 bar on both the diagrams, and I've drawn the corresponding temperature 179.9. So this line over here is at a temperature of 179.9, but we are looking for a temperature of 150 degree Celsius. So this line originally drawn is for 179. If we were to draw a line of 150 degrees Celsius, it would be below the original line. So this line is of 150 degree Celsius. So this line below would be below 179.9. Now where does 150 degrees Celsius and 10 bar coincide? So 150 degrees Celsius and 10 bar coincide in the subcooled region. So state 1 in part A was in mixed liquid vapor region. In part B, it is in the subcooled region. So if we apply the same logic to the TV diagram, so in the TV diagram we are looking for 10 bar pressure. This is the line of 10 bar. So 150 degrees Celsius would be somewhere here below the 179.9, and this is again subcooled region. So let's start solving part C. So in part C, we have 100 degree Celsius and 0.5 degree bar. So the temperature is 100 degrees Celsius and the pressure is 0.5 bar. So the first steps again, we draw the TV, we draw the PV diagram, and we draw the line of constant pressure, we draw the line of constant temperature. Now, if we consult the tables, so if we consult them, so let's go towards the tables. Can all of you see the tables?
Yes, sir.
Yes, sir.
Okay,
Yes, sir. Yes, sir.
okay.
Yes, sir.
So if we go towards table A2 again, so on table A2, corresponding to 100 degrees Celsius, the pressure is 1.014 bar. So over there, so if so this is line of constant pressure, this is line of constant temperature. So if this is 100 degrees Celsius, this is line of 1.014 bar. And if this is 1.014 bar, this temperature is 100 degrees Celsius. This is what we expected. We all of us know that the boiling point of water at atmospheric pressure is 100 degrees Celsius, and the atmospheric pressure is 1 bar, or more accurately 1.014 bar. This is what we expected. Now coming back to this question, so we are in this question we have to locate 100 degrees Celsius and 0.5 bar. So this line that we have drawn on the left is for 1.014 bar. So if we draw the line of 0.5 bar, it would be below 1.014 bar. Okay, so now where does 100 degrees Celsius and 0.5 bar intersect? So they don't intersect in the superheated region, they don't intersect in the liquid vapor region. But if we extend this line, so 100 degree, just a second, so we had to draw 100 degrees Celsius and 0.5 bar. So just a second. So 100 degrees Celsius, so 100 degrees Celsius and 0.5 bar. So 100 degrees Celsius is this temperature here, and 0.5 bar is this line over here. So 100 degrees Celsius and 0.5 bar intersect in the superheated region. Now if you look at the right diagram, 0.5
Off
bar,
हो गया.
0.5 bar, sorry,
Screen sharing off हो गया sir.
so I would repeat that initially we had drawn the
Screen is share.
Show नहीं हो रही sir.
हो गई सर.
so initially we had drawn, so I will just erase this. So temperature 100 degrees Celsius and pressure 0.5 bar. So first thing that we draw the axis, and then we'll draw the line of constant pressure and line of constant okay. So we have to locate 100 degrees Celsius and 0.5 bar. We used the tables and we found that if the temperature is 100 degrees Celsius, the pressure is 1.014 bar. So if the temperature is 100 degrees Celsius, this pressure is 1.014 bar. Now our temperature, but we know the pressure is, for our question, it is 0.5 bar. So if we were to draw line of constant pressure of 0.5 bar, it would be a line below 1.014 bar. So where does, so this line is of 0.5 bar. So where does 0.5 bar and 100 degrees Celsius coincide? So they coincide in the superheated region. Superheated region, we have the temperature of 100 degrees Celsius and the pressure of 0.5 bar. Similarly, in the right hand diagram, if we look at so 0.5 bar, so this line is 1.014 bar. So 1.5 would be somewhere below. So 0.5 bar and 100 degrees Celsius coincide in the superheated region. So what we just did is, it is common sense as well. Why? Because we know that the boiling point of water is 100 degrees Celsius at 1 bar. If we decrease the pressure, what will happen? It would go towards the superheated region. Now let's look at part D. In part D, we have a temperature of 20 degrees Celsius and pressure of 50 bar. So if we draw the vapor domes, and we draw the line of constant pressure and line of constant temperature, now if we go back to the tables, so 20 degrees Celsius and 50 bar, I want you to remember the temperature and pressure. So the temperature is 20 degrees Celsius. So the temperature is 20 degrees Celsius. If you look at this table in the middle, we have temperature 20 degrees Celsius and the corresponding pressure is 0.02339. Remember this bar 20 corresponding to 20, it is 0.02339. If we go back to our drawing, so basically what we are saying is that if this temperature is 20 degrees Celsius, this line is of 0.02 bar. But we have, what do we have? We have 50 bar. So if we draw a line of 50 bar, it would be very above the, it would be very above the 0.02 bar. So this is the line of constant pressure, which is of 50 bar. Now where does 50 bar and 20 degrees Celsius exist? So they exist, so 50 bar coincides with 20 degrees Celsius in the subcooled region. So if we apply the same logic on the left hand right hand diagram, so if this 20 degrees Celsius, this temperature, then this pressure is 0.02 bar, and we have to draw so we have to draw line of, so 50 bar and 20 degrees Celsius. 50 bar is very above, so 50 bar and 20 degrees Celsius would coincide in the subcooled region. Now the last part, part E, we have pressure 1 bar and temperature is -6 degree Celsius. So again draw the TV and the PV diagram. Now if we go to the tables, so on the tables we cannot find the temperature -6 degrees Celsius, which basically means that it is solid, that the temperature is so low it is that it is ice. So the temperature is so low that it is ice, and that is also common sense that at a pressure of 1 bar the melting point of ice is 0 degrees Celsius. So if we have a temperature which is even lesser than that, it would be -6 degrees Celsius. So in today's class we learned that how to find properties, how can we, with the help of properties, we can define a state. So once we know pressure, temperature or specific volume, we can consult the tables to find properties.